Hi everyone, my name is Sandeep. I work as a software developer at LSEG, and uh, yeah, so today is going to be my first talk at a C++ conference. So please forgive me if I make some mistakes. So today's talk is about C++ value categories in action. Um, the, the reason why I picked this talk is because value categories almost seem like we understand them, but when we try to look at the certain rules that are behind all the different value categories, we tend to understand them, but we mostly misunderstand them. So I hope it gets clear by the end of this talk today. Okay, a little bit introduction about me. I'm from India, but I live in Japan for the last 12 years, and I'm married. I have two children, and when they allow me to go out and play with myself, I try to play some cricket and like to go for some runs. So coming up today's talk, firstly we will discuss, of course, what are value categories. Then we will talk in depth about various kinds of references we have in C++11 and how we can, if there are multiple overloads available for all these references, how the overload resolution happens, what is the priority over there. And shortly after that, we will also talk about move semantics and universal references. And in the end, we will look into the best practices around these concepts, which will hopefully give you all idea as to what you can immediately improve in your code. Okay, so a little quiz time here first. So we have a class which has a vector of resources here. And we have two overloads, add resource and add resource. One which is taking a const lvalue reference, and the other which is taking an rvalue reference here. So nothing fancy, it's just the standard code. So here, in this case, which overload is called? Yeah, first one, no surprises there. Yeah. It's copying the resource. So next we have here B which is rvalue reference. And then when we call add resource B, which overload gets picked? One, yes. Everybody one? Okay, I guess you all pretty well understand value semantics already. Okay, so yeah, one is called here in this case. For those of you who thought it two is also possible, B, the type of B is an rvalue reference, but when you refer to B anywhere outside of that statement, the value category of B is lvalue. This is confusing in the beginning, but once you know it, you know it. It will not be confusing at all. So, yeah, so in this case, number one is called. So here, which one gets called? One or two? Two, yeah, because it's a temporary. Yeah, just what we discussed here. Okay, so why should we learn about value categories? I mean, for those of you in this room, you have no other option but to learn for the next 1 hour because you're here. Other than that, I personally feel like once you understand value category, it can definitely form a very good base for you to dive into more concepts like move semantics, copy elision, or forwarding references, or any other piece of like, if you look at the standard library code, for example, you would see references all over the place. And if you don't fundamentally understand what is a value category, it'll be difficult to understand modern C++ code. That's my opinion of it. Yeah, apart from that, when you try to write something and compiler throws an error at you saying that an lvalue reference cannot bind to an rvalue, you should exactly know what that is really about. So understanding the compiler errors efficiently effectively will definitely help you in understanding where you're wrong. And also it definitely helps you write semantically correct and performant code. Um, So yeah, I hope we all want to learn about value categories. So what are they really about? What are value categories really about? Any guesses? Like, what are they really about? Are they about like the objects, types? What are they really about? Okay, let's check first what are they not really about. They are not about objects or variables. They are not about the types. They're not directly about lifetimes as well. Yes, lifetimes have a kind of role to play in what a value category is, but a value category is not really directly about about lifetimes. So what are they really about? They're about expressions, expressions, and expressions. Yeah. So, yeah, when we are learning a new language, I don't think we spend a lot of time in reading a chapter called as expressions, right? Like, neither did I. So, when I learned that they're really about expressions, then I went on and looked as to what really are expressions. So the standard says an expression is a sequence of operators and their operands that specify a computation, and that it produces a result and can also have a side effect. Like for example, std see out, and when you print a value, the side effect is that you see something on the screen. Okay. Uh, so in short, any piece of code that computes to something and has some side effects, you can say that it is an expression. And value categories are really about expressions, okay? They do not apply to other parts of the code. So in your entire code base, you could say that value categories apply to almost 60 to 70% of the code, because all of those are expressions and rest are not expressions. So here, for example, on the left, you can see what are expressions, like 5 plus 3. This evaluates to 8, of course. So this is an expression. And yeah, string high, a function call, not the function declaration itself, but when you call a function, that is considered as an expression. So what does this really mean though? So when you compile your program, and when your compiler goes and reads your code, it classifies each and every line of the code into different constructs. So when it does that, when it looks at this particular part of the code, it basically says that, okay, this is an expression, okay? And how it keeps track of expressions is what something we'll just look ahead. So yeah, on the right, you see some statements which are not expressions. Yeah, and value categories apply only for expressions. Enough of expressions. Let's keep moving forward. So, but again, expressions. Okay, so expressions, they have two independent properties. So, like I said, compiler, whenever it finds an expression, it keeps track of two independent properties. The first is type, and the second is a value category. Okay, so yeah, what is a type? I think we all know what is a type. It tells you what kind of value it is, whether what is the type of this value, int or constant, intref, intref, etc. So the type, obviously it is very clear as to what it means. So apart from that, there is one more property for each of these expressions, which is called value category. So value category is a direct property of an expression. So 5 plus 3, when you look at that expression over there, it has two independent properties, a type and a value category. So what is a type for 5 plus 3? It returns an int. So the type is an int. But what is the value category over there? So the it is a temporary, so it is classified as a rvalue. So we will come to that, but a compiler keeps track of both these things. That's what we need to really understand about. Okay, so before we dive into the value categories and then understand what are the different types of value categories we have, let's just look at prior to C++ 2011 as to what kind of value categories we had. And in order to understand them, let's just look at how a vector used to work before C++ 11. I think we all know how a vector works. Basically, initially it has some capacity, and then when you keep on adding elements to it, it gets expanded. The end pointer, it keeps on moving towards the end, and once it reaches this point, uh, when you try to insert more elements to it, it needs to reallocate memory, right? We all know this. Yeah. So after this reallocation, what happens here? We copy over all the elements from the previously held positions to the new positions, right? So I said copy, but in modern C++, a move is also possible. But we are talking about C++ prior to C++11. So at that time, it was only copy. So what is the problem with this? Immediately after the copy, the copied elements are now destroyed, right? So uh, theoretically, it was possible for us to be able to reuse those elements even in the newly allocated vector. We didn't have to completely destroy those elements and then deep copy over them. It was not needed. I think we all know this already, but I'm talking about this because I want all of us to keep this point in mind when we are discussing the further concepts. So this is a problem we wanted to solve in C++11. So here, so again, before C++11, we had two value categories, lvalues and rvalues. So lvalues are basically anything that have identity and which are long-lived. So the value categories are very deep into the C++ genes. Like we got this lvalues and rvalues from C. And rvalues are nothing but temporaries, like literals like 42, string hello, all these are considered as rvalues. And to work with these value categories, we had only one reference type, which is tref. We call it as lvalue reference. So what about this lvalue reference? It binds to lvalues. That's why it's called an lvalue reference. So you can see the example, int x equals to 42, and you can declare a lvalue reference variable and just directly bind to x, right? So can we also bind to rvalues using this tref? You could bind to rvalues only by using a const tref, right? So what is the problem with this? We are unable to bind to rvalues. And why is that important? If you just go back here, just imagine. So the initially allocated vector is going to get destroyed. So if we want to reuse the elements from that vector, what was stopping us prior to C++11? I think number one, it's that we did not have a way to express that these elements are going to expire. Okay, so we just had lvalues and rvalues. When we said lvalues, we mean that these are objects with identity which we want to keep using forward. And when we said rvalues, what we really meant was that these are temporaries and going to get destroyed soon. But we did not have a way that we did not have a way to express that we are done using these objects and these are ready to expire and somebody can take them. So yeah, these are the some problems, our value binding problems. So we had std string, so it just copies the values. So we have const lvalue reference here. It binds to rvalues, but you are not able to mutate them, in the sense like if you want to steal the resources from these rvalues, you're not able to do it. And then if you try to do something like this, std string ref, which is an lvalue reference, it would not bind to rvalues. So prior to C++11, this was a bottleneck which was preventing us from binding to temporaries or binding to expiring values and letting us steal the resources from there. So the two category system was limiting us in order to achieve things like move operations. Yeah, we just discussed. So there are two problems here. First is that we are not able to mark objects as expired. And second is that there was no way for us to bind exclusively to rvalues. So let's first talk about the first problem here. So like I said, we did not have a way to express that, okay, this particular object is going to expire, so it is up for stealing the resources, right? Members from the standard core committee, they all sat in the room, they wanted to solve this problem. And then when they jotted it down on the board as to what kind of values how many different value categories are possible and they're needed, they came up with a diagram like this, where we had A value, B value, C value, D value, E value, F value, G value, so many values here, right? Of course, this is not going to fly. So they sat down, and when they looked at what are the two properties of these different value categories that we need to focus on, then they came up with this diagram. So it clearly tells us that we have two properties, I and M. I stands for identity, and M stands for movable nature of it. So all the different types of value categories, when they examined, we just need to really communicate in terms of two parameters, whether the value, the result of the expression can be moved or not, and secondly, whether the result of this expression has an identity beyond this expression. Yeah, so identity and movable nature. So what is identity? Like I just explained, does the expression refer to an object with persistent identity beyond the line in which you are using this expression? The movable nature of it, whether we can safely move resources from this expression, is it safe to steal the resources from it or not? Yeah. So we have two properties. Either you can have the identity or you cannot have the identity. Either you can move it or you cannot move it. So four combinations are possible, but we have five value categories. So how is that? So yeah, I just listed down the possibilities here, whether when you write an expression, the result, how do you want to communicate about the nature? How does the result behave? Whether it is identifiable or not identifiable, whether it is movable or not movable. Yeah. So here, I and M, it means that the result of the expression is identifiable but not movable. So capital M, by that I mean that it is a negative, so it is not movable. And such categories are L values, and they have always been the case, because L values are like the variables like X, which you are not done using them. So they have a persistent identity even beyond the expression. You can refer to them using ampersand X, for example. But they are not movable because we are not done using the resource by ourselves. So these kind of values, we want them to remain as L values. Uh, so next we have a PR value. What is a PR value here? So they do not have in the expression, the result of the expression, it is not persistent in the memory beyond this expression. So you cannot take the address of it. So they do not, they are not identifiable. So that's why it's a capital I. But the resources can be stolen. So if you want to steal the resources and not do a deep copy from a temporary, it should be possible to do. So they are definitely movable. So these kind of values, we are calling them as PR values. So PR values prior to C++11, what we call as R values, we're just calling them as PR values now. Okay, so P stands for pure R values. And by the way, in L value, when we say an L value, most commonly we think that L stands for left-hand side of the expression, so it's left-hand side values, but L stands for locator values, which mean to say that they are locatable in the memory. They are persistent in the memory, they are locatable. You can locate them whenever you want. So this new category, which is xvalue, is what was introduced in C++11. This is solving the problem number 1 from the two problems we discussed, where we want to express that an object is expiring. So it is up up for grabs. So if somebody wants to steal the resources from this, you can do it, right? So what is this value? It's I and M, both identifiable and modifiable values. And there are also non-identifiable and non-movable values, which make no sense, and we can just ignore them. Like there is no particular value category for it. Yeah, so we discussed that we discussed three value categories: L values and X values and PR values. I hope these three value categories are a bit clear than they were before. Uh, but a generalization was also required, because whenever we wanted to, in the standard, whenever we want to talk about how the properties of identifiable expressions, we didn't have to always specify L value and X value. So we came up with a generalization stating that these are called GL values. And the same for X values and PR values together, we're calling them as R values. Yeah. And any questions so far? Okay. Yeah, so we have 5 value categories, 3 of which are primary value categories: L value, X value, and PR value. And 2 are generalizations: GL value and R value. So like I said, we borrowed the concept of value categories from C, right? So it is really very deep into the genes of C++. Like from the time when we started doing C++ 98, we had L values and R values. So when we were defining all these new kinds of value categories, it was really important to retain the meaning of what an L value and what an R value really meant. So that definition is still valid. So historically, so what is an L value? Which is locatable in the memory and which is persistent beyond the expression, but whose values you cannot steal, right? So that is still the case. And what is an R value? R value is a temporary, which is soon going to expire, right? So there are so in this there are 2 divisions. One are temporaries, which were never materialized into objects, so that's why they are going to expire. And second is the kind of objects which have memory, but they are also going to expire soon. So this is a new category which we want to be considered as R values itself. So even though we have X values and PR values, the fundamental notion of what an R value is, it still holds for both of them. So that is why the naming is like this. Okay, so yeah, X stands for expiring values here. There are 2 other popular representations of value categories. On the left, we have a Venn diagram which very clearly shows that L value, X value, and PR value are 3 different primary value categories. Just take a moment here to look at the examples and see why they would be considered as L value or X value or PR value. In int x equals to 42, the whole line itself, it's a statement, it's not an expression, but only the X part here is an L value. Yeah, when you're referring to a star pointer here, yeah, it's an L value because it has an address. And you will continue to use it, so you cannot steal the resources from it, right? Same goes for array of 0 when you dereference an array, and obj.member. Yeah, all these are having a persistent memory, and therefore they are identifiable but not movable. That's why they're considered as L values. Yeah. Next, we have X value, stood move X. This is mainly what an X value is. In most of the cases, it's just stood move X. We will talk in depth about what stood move does and what are move semantics and all in the coming slides. But if the concept of L value, X value, PR value is not very clear, I hope in the future slides you might get lost. So any questions here? No? Okay. Yeah. Yeah, PR values are temporaries. 42, it's a literal. That's why it's treated as a temporary. We have true, we have widget. function call, x plus y, all these are temporaries. So I have three dedicated slides to talk about each of these values one more time before I dive into move semantics and universal forwarding references. Yeah, these are the two different representations that are very commonly used to talk about these value categories. Yeah, so let's look at some examples, which some of which are straightforward, some of which you might be pleasantly or unpleasantly surprised a little. Yeah, this one, int x equals to 42, x is an L value. So A equals to B. So L value is just not about the objects or types or variables. We just talked about it in the beginning, right? So A equals to B is also an expression, and even this has a value category, right? So why is it an L value? Because A equals to B, it returns A, okay? So which has a persistent location in the memory beyond the expression. So that this is the reason why you're able to do A equals to B equals to 10, and the 10 would be assigned to both B and A, because B equals to 10 would return B, and that B you can assign it to A, and the result is A itself, okay? So yeah, understanding value categories again will try to explain some things that we already know and some things we don't. Plus plus A, it's a pre-increment operator. So it is an L value because at the end of it, it returns A after the value is incremented. If you notice, post increment is not here. So post increment is not an L value. We'll just see that in the next slide. Yeah, referencing a pointer, I think everybody believes that it is an L value. Same is the case with accessing an array element, and a string literal, not a string, yeah, string literal is also an L value. So this might be a little surprising. But it is an L value because they have a persistent storage, and you can access the address of hello as well. It is for pure string literals. It is not for std string. It's a pure string literal. So yeah. More examples here. If you have a function foo, you can catch the address of this function with ampersand, and that's why the function pointers are L values. Yeah, and if you are returning by a reference like intref, in that case, the return values are also L values. Okay, and just in case L values have identity, they refer to a persistent memory location. You can take the address with ampersand, and it's persistent beyond the expression, and they cannot be moved from. Next, we have prvalues. Again, let's just look at what these are. You cannot take its address because they are temporaries, but you can move from them, right? And almost all temporaries are classified as prvalues. Literals and computed results also are classified as prvalues. So 42, true, null pointer, all these are literals. Hence, these are prvalues. So any function call whose return type is non-reference, for example, here get some a comma b, it results a plain int. So all the return values are classified as prvalues when they do not return a reference. So any non-reference return type is considered a prvalue. Same thing when you are doing a substring of like a string, then what the resultant object is a prvalue, like we just discussed. A plus plus. So A plus plus is interesting. Plus plus A is an L value, but A plus plus is a prvalue. Why is it so? Because it increments and returns a temporary with old value of A. So it does not return A here. So it increments and results. It returns a temporary with the old value of A. So that is why A plus plus is a prvalue, while plus plus A is an L value. Like again, yeah, we are having these 3 slides for each of these values, and we are talking this is an L value, this is an R value. We are doing that because when you use this expression in a particular context, when you say it is an X value, it has a meaning to it. So the caller of this, the receiver of this, he will basically try to either steal the resources or not based on the value category of it. So that is why it is important to know like different possibilities of what this can be. Like if you're using a++, you should know that it is an L value, it is a PR value, and that it cannot bind to an L value reference. So these are the things we should know. That's why we're just looking at various examples here. Yeah, few more examples. A plus B computation and ampersand A. Ampersand A is also, you cannot do like ampersand A in C++. So we have ampersand A classified as PR values. This pointer is also a PR value. And the lambda objects are also PR values. So a lambda is nothing but a closure type object, which is a temporary closure type object. So unless you bind to it, it remains a temporary. So these are also considered classified as PR values. Next, we have xvalues. Xvalues are expiring values. They have identity and also can be moved from, like how we discussed before. So std string s equals to hello. So s itself is an L value here. But when you do std move s, so the std move s altogether, it's a x value. Okay, s itself is a L value, but std move s altogether is an x value. Yeah, so when you try to access a member function of an x value, the returned object is also x value. So here is an example for that. Yeah. We said there are two problems before C++11. One is that we are not able to express that particular object is expiring. So that we have solved by introducing x value. So when we say, okay, the value category of this expression is an x value, it is very easy for us to communicate to the compiler that it is going to expire, right? So, but how do you catch those values and do something with them, right? The C++ type system, like we discussed before, it only had tref and constref. Tref wouldn't bind to any kind of temporaries, for example. And constref would bind to it, but it doesn't allow you to modify those values. Okay, so C++11 introduced tref. I would say like this is the hero of C++11 for me at least. So this introduction of tref, which is called as an R value reference, is very important because it exclusively binds only to R values. So when we say R values, we have two value categories inside the R values, which are X values and PR values. Both of them are going to expire soon, and you can steal the resources from them. So having a R value reference like tref, which can bind only to these two value categories, helps you do something with the expiring values like stealing the resources, etc. Examples of tref. First of all, the syntax is the type and ampersand and the variable name, for example. It binds to R values, we spoke about it. Yeah, it provisions stealing of resources. So because of this R value reference introduction, it is now able to implement move semantics and perfect forwarding. We'll look into those a little later. So on the right, we have examples of using an R value reference. So int ref R1 equals to 42. So what is 42? What is 42? It's a literal, so it's a PR value. So since it is a PR value, in order to bind to it, we have to use a R value reference. So in R1 is R value reference to the literal 42. Okay. So a little bit about this. In int ref R1 equals to 42, the int ref is the type of it. Okay. So this needs to be very clear in the heads that int ref is the type. The value category of R1 itself is again a L value. If you use R1 beyond this line anywhere in the code, R1 is still an L value because it is a named variable. Okay, but the type of it is a R-value reference. I'll keep mentioning the same point again and again because it takes a little bit time to register if you already don't know, if you don't know that already. Again, in line number 7, you can see that create a, it's a function that's just returning a by value. So anything that is being returned by value is considered as a PR value. So we are again catching that using an R value reference here at line number 7. So this is one example use case. Prior to C++11, what would happen at line number 7? Create a would give you an object, but that needs to be copied into RR. So we will be having two. I mean, you could not write anything like line number 7 in before C++11, but if you just had a RR equals to create a, then we would have two copies of a, which we don't need anymore now. Yeah, so I hope everyone understood what is an R value reference. R value reference is to bind exclusively to R values. So here we are. We have L value reference, const L value reference, same as in C++03, but we have two more new additions, which are trefref, which is an R value reference, and we have const trefref. Const trefref is almost useless because it doesn't make sense semantically. Because when you say trefref, it's an R value reference. It means that I want to steal the resources, but the object is const, so you cannot steal the resources. So it is of no use to us. But semantically, it is possible, so it is there in this slide. Here are the binding rules. One, and when I say first and second, that's the priority. If, for example, an L value can bind to both an L value reference and a const L value reference. So, but the priority is 1 and 2. So X value and PR value, the rules are same for both. So you could just think them of together like R values. So they would bind to tref first if it's available. Otherwise, it would bind to const tref. So binding to const tref is nothing but the same behavior as to before C++11, right? So temporaries, if they are binding to const tref, it means the objects are not modifiable, so you just have to make a copy. But if there is a move constructor available, and if you're able to bind to tref, which is an R value reference, it means that these are exclusively marked as R values, and you are safe to steal the resources from it. So it is possible to steal. Yeah. Yeah, that brings us to move semantics. So now we have two additional tools in C++11 that we did not have in 03. One is xvalues and the other is tref, right? Okay. So what is the idea? It is to reuse the internals of the temporary or the moved from object. So just remember the vector example that we discussed where the elements were going to get destroyed. And if we want to reuse the internals of those vector and do something about it, it is now possible because we can bind to them. First of all, we can mark them as X values. And secondly, we can bind to them exclusively using R value reference and then safely steal from it. So doing such a thing is possible. And yeah, we'll just look at an example. Move semantics is the driving idea behind making changes from just 2 value categories into 5 value categories and introducing R value references. So achieving move semantics is the main reason for it. So stood move marks an object as expiring value. So you have an L value. So you were using it until now. Now you say that, okay, this is, I'm done with it. Now I want to transfer the ownership, or I'm done with the resources. So I want to give these resources to somebody else who wants it. So how do you express that? You say stood move on that object, right? So stood move, what does it really do? It doesn't move anything. I think so there are so many talks, especially on move semantics, explaining the same thing, that stood move doesn't do anything. It is just cast to an R value reference. right? But with everything we spoke so far, when you look at the implementation, I hope it hits everyone differently, in the sense like you exactly understand what is happening here. So here we have an R value reference to T. Actually, it's exactly not R value reference to T. We'll just talk about it in the next slide, because T in the context of a template, it's called a universal reference. But that's just one extra thing that we are going to look at. But yeah, for now, you can just look at the implementation. What we do is we are casting it to an R value reference. How are we doing it? First, we are removing any kind of references that T might have. So remember, when we say we are casting it to an R value reference, we are talking about types. We are not talking about value categories, right? So what is the type of T here? It can be either L value or R value. In both the cases, we are removing any references to it and then just casting it to ref. So that means that we are removing whatever the references that these values have, and then we are typecasting it to an R value reference. That's exactly what studmove is doing here. Okay. So everything we discussed so far, let's see what all it boils down to. Here is an example of a move constructor, which is using tref. Okay. Yeah. So here you could see that because it's a tref, it binds only to expiring values or temporaries, both of which are movable in nature. So what do we do here? On line 13, you can see that you are initializing your internal data member with just updating the pointer with the other, right? And you are marking the pointer of other with null pointer, meaning that you are stealing the resources. So we keep talking about stealing the resources, and this what it means is exactly this. You just take the resources. You don't do a deep copy of all the contents of this pointer. You just take the pointer and assign it to yourself and invalidate the pointer at the other object, right? So yeah, we solved the problem. There were two problems. So we introduced trff and introduction of xvalues together. We are now able to have a way wherein we can implement something like this, where we have a move constructor and bind exclusively to R values so that we don't have to do the deep copies. For example, you can see on line number 9 here, uh, prior to C++11, what used to happen? We just had const lvalue reference for which the PR values or R values would bind to, and there was no other way than to do a deep copy, because we cannot modify the moved from the other object. I hope this is clear to every one of us. So quiz time again. So we have 5 different scenarios. The first one, how many objects are constructed here? Why 2?
On the right side, and then you have a copy of some new
So here, just one object is created, because we have so in C++17 we have guaranteed copy elision, for example. So here the temporaries so buffer 42 is a temporary, but there is no need to copy it over. It's a PR value, so it is directly constructed at the caller side. So B1 is directly constructed, and we have only one object that is created. So number 2. Yeah, 0. No new members, no new objects are created. We just have one move operation. So yeah, 0 and 1. And at line number 3, yeah, 1 is created and 1 move, because we have stood move over there. right? So what is the difference between 1 and 3? So here we have a PR value, but we are doing a stood move on that. So because of which move constructor is also invoked. Number 4, we have create buffer. The definition of create buffer is on the right. So we're returning a const. What would happen in line number 4? Yeah, just one. Const wouldn't do anything crazy here. 5 is interesting. What would happen here? So create buffer, we are returning a temporary, but it's a const temporary. And then we are trying to do a stood move on that. So what would happen in this case? No, it would run. Yeah. So, okay, with everything we have learned so far, just let's try to approach this and understand what is happening here. Because so we are getting a temporary. Temporary is a PR value, and the type of it is uh, a const temporary, right? So const temporary, and then you're doing a stood move on that. So it is a const R value reference, right? We have a const R value reference here because stood move typecasts it to a const R value reference, but sorry, it typecasts it to a R value reference, but there is also const here. So it's a const R value reference. But if you look at our move constructor, uh, so here, because it is an R value reference, there are two candidates, right? We have const L value reference and an R value reference, tref and const tref. But because it is const, tref is not a candidate anymore, and we would bind only to const tref. It means we have one new and one copy. So this is not ideal. So generally, as a good coding practice, we should not be returning const temporaries. So if you try to do that, then you would be invalidating move semantics. Yeah. Yeah. So the question was if stood move changes the const nature of the expression of the object, but it does not. The CV qualifiers are retained, and only the reference nature of the type is changed to make it R value reference. More questions? Yeah. So the question was if you implement stood move in a similar way, would it work or not? Yes, it would work. It is a library function which is available. But if you want to write your own move, you can most definitely write. Yeah. More questions? So how does return value optimization work with value categories? Is that your question? Yeah. So, return value optimization itself is a big topic. We have RVO and RVO and different variations of it. But to put it simply, uh, C++17 mandates that all PR values should be directly constructed at the caller's side, and any kind of copy or move should be elided. That's the rule from C++17 copy elision standards. So if you have a PR value and if you are using an assignment operator, instead of doing a copy or move, instead it directly constructs the object at the source. So uh, that's how the copy is completely elided. Yeah, because it's a temporary, it's going to expire. We don't need to first create it and then copy or move it. Instead, we can just directly do it at the source. So that's the optimization, which is RVO in the C++17 copy elision. That's what we refer to it as. Okay, I just have 9 minutes, so I want to finish my slides. In the end, I'm happy to take more questions. Oh, okay. So tref, when t is template parameter. Uh, so uh, we just talked in length about what is tref, that tref is an R value reference, but tref is not always an R value reference, right? Except when it is a deduced type, it is an R value reference, but in the deduced context, it is called a universal reference or a forwarding reference. Okay, so here we have two examples. In the first, the T is deduced, right? The template code itself does not have any type. to it. When you try to instantiate this template by using some concrete types, then the T is deduced on the run. So this is a special case. Uh, because in library we want to be able to write generic code which works for all kind of value categories. We created this one exception. Okay. Uh, yeah, here it is called universal reference, and the rules are slightly different from what the rules are for R value references. So just keep that in mind. We'll talk about the rules and what is special about this. Okay. Yeah. We need to understand a little bit about reference collapsing here. What is reference collapsing? So we have this function f, which is trefrefx, and where t is a deduced type. So what is t? T is a type. So in C++11, we have plain types, which is like int, float, or objects, and we have two reference types, which is like intref or string ref, or you can also have R value references, right? So the t can be any of all these things, but there is also a ref after t. Okay, so if you're passing a R value reference to this template function, what will happen? Because the type of the R value reference is trefref, it is going to be trefref, and then there is ref. So tref, right? So this is when the reference collapsing rules come into the picture. So the standard says that. Yeah. I mean, I think the table is self-explanatory here. So if L value reference and L value reference are together, it results in an L value reference. It collapses into an L value reference. If it's L value and R value reference, the result is an L value reference. The first two are not directly related to this example of universal references, because only a templated function with tref is considered as a universal reference. Okay. So in this case, what happens? So L value reference, when you collapse it with an R value reference, you would get an L value reference. And R value reference and R value reference together, when collided, it results in a R value reference. So yeah, it takes more words to explain, but a picture is worth 1,000 words, they say. So you can just get it from there. So you have int x equals to 10, f of x, and std move x. So in this case, when you say f of x, what would happen? Just an example here. When you say f of x, what would happen? So x is a L value, right? Yeah. So when you are passing an L value, so the T, template parameter T, is deduced as L value reference, and then when it when it collapses with ref, what it happens? What it turns out to? An L value reference, right? So the universal references can also bind to an L value reference and retain the same nature of it. Okay. In the second example, f of std move of x, what happens? Std move of x produces an x value. X value has a tref, and when you call it with the template tref, you have is like int ref from here, and it collapses with tref, which is like which results in an R value reference. So this template code, because of this reference collapsing rules, which are applicable only when T is a deduced type, can bind to both L values and R values. This is good, but this is also dangerous, right? Because it can, if you're not careful enough, you could bind to both L values and R values and do move, and we don't want to do that, right? So if the explanation was not very clear, here is one example. We have like foo3, foo x, and foo std move x. So in the first case, T is deduced as int, and tref becomes int ref. In the second example, when you do foo of x, x is an L value. So T is deduced as int ref, and tref becomes int ref because of the collapsing rules we just discussed. Okay, and we have the third value. I explained all these three in just the previous slide, so I'll just skip this one. Yeah, so we discussed that a universal reference can bind to both L values and R values. I hope it is clear that it can bind to both L values and R values. So because it can bind to both L values and R values, what you're going to do with the argument is really important. If you just do something like collie and just use the name by itself, what is ARG here? What is the value category of ARG? What is the value category of ARG? L value, right? Because we are just referring to it by name. So it is an L value. So we don't, so originally what we passed is an R value, but because we are just referring it by name, it becomes an L value. We don't want to do that. So this kind of code is bad. So instead what we should do is use stood forward. So stood forward, it preserves the value category of the passed in argument, and strictly it should be used in the cases where T is a deduced type, so that you can forward the arguments along by preserving the value category of the passed in objects. So, okay, so we looked at this example in the beginning. We had a pool class with two different functions, one for constant value reference and R value reference. So if you want to write a generic code for it, how can we write that? So here we can just declare that declare the argument as a template argument. Function template arguments T, ampersand, ampersand, ref. So what is the value category of R here? It's a universal reference. It's a, what is the type? Sorry, I meant to ask what is the type of it. It is a universal reference, right? So it can bind to both L values and R values. So you can just do stood forward here. In this way, both the functions on the left, you can just have one function that could bind to both and also perfectly forward the arguments. So stood forward and universal references should be used together. But if it is plain types, you should always use stood move or copy. So this should be very clear. So I think I just have a few minutes here left. So let's just look at different best practices surrounding the value categories. So here, when you're returning temporaries, try to avoid using stood move. Just return them by value, because like we just discussed in C++17, copy elision makes sure that the values are directly constructed at the caller's storage. So something like on the right, where you're trying to do stood move return, is not very great. So there are two possibilities, right? Like when you're trying to copy the values into something, you can bind to the L values using std string s, or you can bind using const std string ampersand s. So directly copying in the argument and then moving is better than the second one, because when you have a PR value here, for example, the argument, what would happen in the second case? Yeah. So extra copy happens, right? First, the PR value is created, and then when you copy, a new copy is made. So there are two instances of this object. But in the left, there is one object creation, and then move happens. So it is efficient when you have PR values in the argument. So only use stood forward if T is a deduced type. If not, things can go really wrong, because in this example, we have an L value reference S, and if you try to do stood forward on this, what happens here? It is because stood forward, if you look at the implementation of it, it tries to cast it into an R value reference. Why does it do so? Because it is relying on the reference collapsing rules. So if it was a template parameter, then L value reference and an R value reference, when collapsed together, it would result in an L value reference. So it would retain the value category. But here, in this case, because it is not a template parameter, and if you try to do stood forward, it would act in the same way as stood move. So an L value, if you do a stood forward on L value, it is really dangerous. Yeah, and I think even this is covered in so many talks before. Uh, Move operators and move constructors, both, you should mark them as no except. If not, then strict vector implementation, for example, it would try to, it checks whether the move constructor gives you a strong exception safety or not. If not, then it will fall back to the the copy versions of it. So it is important to mark move constructor and copy assignment operators with no except. Yeah, it is directly related to the previous slide as well. So the vectors also internally implement something called as stood move if no except. So they check whether the move constructor has strong exception guarantees or not, and only then it uses move. Otherwise, it uses copy. Yeah, this brings us to the last slide. We discussed about value categories. We tried to understand them. I hope it is clear. So you can optimize your things. You can optimize your code using move semantics. Uh, and wherever the T is a deduced type, please make sure to use stood forward. And we also discussed best practices and common pitfalls. So try to avoid them in your code. And yeah, I hope everyone here, you understood something new from this session. And thank you so much for attending.